20.5 Distribution of Molecular Speeds. In this session, we will explore several key topics regarding how molecules move and distribute themselves within a gas. Our outline includes the Boltzmann distribution law, the thermal excitation of atomic energy levels, and the Maxwell-Boltzmann speed distribution function. We will also define and compare different characteristic speeds, such as the root mean square, average, and most probable speeds. Finally, we will look at evaporation as a cooling process to see these statistical principles in action. To begin our introduction to molecular distributions, it is important to recognize that up until now, we have mainly focused on the average values of molecular energies. However, molecular motion is extremely chaotic. In atypical gas, molecules undergo billions of collisions every second. Each of these collisions constantly changes the speed and direction of the participating molecules. Because of this complexity, we use distribution functions. These mathematical tools allow us to determine the relative number of molecules that possess specific characteristics, such as a certain range of energy or speed, rather than trying to track every individual particle. The Boltzmann distribution law is fundamental to understanding these systems. We define a distribution function called the number density, represented as n sub v of E. Here, n sub v of E multiplied by dE gives us the number of molecules per unit volume with energy between E and E plus dE. The law states that the number density of molecules with energy E equals a constant n0 times the exponential of negative E divided by the product of the Boltzmann constant and the absolute temperature. This means the probability of finding a molecule in a particular state decreases exponentially as the energy increases. Effectively, thermal agitation at a given temperature is what excites molecules to these higher energy levels. A common pitfall is misunderstanding how the distribution function is applied. It is defined in terms of a range from E to E plus dE, not for a specific exact energy, E. This distinction is crucial because the number of molecules in any sample is finite, while the number of possible energy values is essentially infinite. Consequently, if you were to look for the number of molecules with one exact, precise energy value, that number may actually be zero. We must always consider a small interval or range of energies when using these functions. Let us look at an example of thermal excitation. Suppose we have a gas at a temperature of 2500 Kelvin. In this simplified model, the atoms can only occupy two specific energy levels that are separated by an energy gap of 1.50 electron volts. 1 electron volt is a small unit of energy equal to 1.60 times 10 to the negative 19th power joules. Our goal is to determine the ratio of the number of atoms found in the higher energy level compared to the number in the lower energy level at this specific temperature. To solve this, we apply the Boltzmann distribution law. The ratio of the number density at the second energy level to the number density at the first level is equal to the exponential of the negative change in energy divided by the Boltzmann constant times temperature. First, we evaluate the denominator term, the Boltzmann constant times temperature, which equals 0.216 electron volts for this gas. By substituting our values into the ratio formula, we calculate the exponential of negative 1.50 electron volts divided by 0.216 electron volts. This gives us a ratio of 9.52 times 10 to the negative fourth power, meaning only a very small fraction of atoms are in the excited state. The man pictured here is Ludwig Boltzmann, an Austrian physicist who lived from 1844 to 1906. He was a monumental figure in science, contributing significantly to kinetic theory, electromagnetism, and thermodynamics. His most pioneering work was the development of statistical mechanics, which connects the microscopic motion of individual atoms to macroscopic properties we can measure. He established the vital mathematical relationship between the energy states of particles and the absolute temperature of the system, a concept that bears his name today. While Boltzmann focused on energy, James Clerk Maxwell derived an expression for the distribution of molecular speeds in 1860. In this model, if n is the total number of molecules, the number of molecules dn with speeds between v and v plus dv is given by the Maxwell-Boltzmann speed distribution function. This function is 4 pi times the total number of molecules, multiplied by the quantity of the mass of a molecule, divided by 2 pi times the Boltzmann constant times temperature, all raised to the 3/2 power. This is then multiplied by the speed squared and the Boltzmann factor, which is the exponential of negative molecular mass times speed squared divided by 2 times the Boltzmann constant times temperature. Looking at the characteristics of the speed distribution graph, we see a curve that starts at 0, peaks, and then tails off. The area of the small shaded rectangle, defined as the distribution function times dv, represents the actual number of molecules within that specific speed range. You can see labels for the most probable speed, the average speed, and the root mean square speed. It is important to note that the distribution peaks near the root mean square speed, and very few molecules possess extremely high or extremely low speeds. Most molecules are clustered around the central values defined by the temperature. Temperature has a dramatic effect on the speed distribution. As the temperature increases, the peak of the curve shifts to the right and becomes flatter. For example, comparing a gas at 300 Kelvin to one at 900 Kelvin, the higher temperature curve is much broader. This shift indicates that the average speed of the molecules increases with temperature. Despite the change in shape, the total area under either curve remains equal to n, the total number of molecules in the system. In the graph shown, that total is 100,000 molecules. Also notice that the root mean square speed is always greater than the average speed, which is in turn greater than the most probable speed. We can calculate these characteristic speeds using specific formulas derived from the distribution function. The root mean square speed is the square root of 3 times the Boltzmann constant times temperature divided by the molecular mass, which is approximately 1.73 times the square root of the Boltzmann constant and temperature over mass. The average speed is the square root of 8 times the Boltzmann constant times temperature divided by pi times the mass, or about 1.60 times that same square root factor. Finally, the most probable speed is the square root of 2 times the Boltzmann constant times temperature divided by the mass, or 1.41 times the square root factor. This confirms the relationship that the root mean square speed is the highest of the three. Let us apply these to a practical example involving a half-mole sample of hydrogen gas at 300 Kelvin. Using our formulas, we find the average speed is 1.78 times 10 to the third power meters per second. The root mean square speed is slightly higher at 1.93 times 10 to the third power meters per second, and the most probable speed is 1.57 times 10 to the third power meters per second. If we want to find the number of molecules in a very narrow range, say a range of 1 meter per second at a speed of 400 meters per second, we find there are approximately 2.61 times 10 to the 19th power molecules in that specific interval. The concept of speed distribution helps explain why evaporation is a cooling process. The distribution of speeds in a liquid is very similar to that in a gas. Within a liquid, some molecules are moving fast enough to have the energy required to overcome attractive intermolecular forces and escape from the surface. When these high-energy, fast-moving molecules evaporate, they leave behind the molecules with lower average kinetic energy. Since temperature is a measure of average kinetic energy, the temperature of the remaining liquid decreases. This is why a wet finger feels cool when the wind blows on it, or why alcohol feels cold as it evaporates from your skin. Speed distributions also explain atmospheric escape. At any given temperature, the distribution depends on the molecular mass. Specifically, lighter molecules will have higher average speeds. This is why lighter gases like hydrogen and helium escape Earth's atmosphere much more readily than heavier gases like nitrogen or oxygen. Over time, these light molecules reach speeds exceeding the escape velocity. This effect is even more pronounced on the Moon. Because the Moon has a much lower escape speed than Earth, gas molecules escape so easily that it has essentially no atmosphere at all. In summary, the Boltzmann distribution law describes how particles are distributed among different energy states based on temperature. The Maxwell-Boltzmann speed distribution function specifically describes the spread of speeds in a gas. We have seen that increasing the temperature shifts the distribution toward higher speeds and creates a broader peak. We also established that the root mean square speed is greater than the average speed, which is greater than the most probable speed. Finally, we learned that evaporation cools a liquid by selectively removing the most energetic molecules from the system. To wrap up, consider these review questions to test your understanding. First, can you explain why the molecular speed distribution curve shifts to the right and flattens out as the temperature of a gas increases? Think about what happens to the energy of the particles. Second, using the concepts of speed distribution we discussed, explain why the Earth's atmosphere is mostly nitrogen and oxygen with very little free hydrogen. Consider the relationship between molecular mass, speed, and the ability to escape a planet's gravity.